Okay, here we go. So we're going to start calculating some Riemann and trapezoidal sums here. There's going to be 4 examples in this video to go through like the 4 different cases, the 4 different types of sums that they could ask you for. Just make sure you capture good notes, okay? This isn't hard, but it is important to know all 4 different types of these sums, and when you're learning them, keeping them straight is the biggest challenge. So if you have good notes, you're going to be set. If you don't have good notes, you're probably going to run into some issues here. Okay. These are super common on the AP exam, especially on FRQs. So it's good to get some practice here and make sure you have a good reference for it. Okay, we're going to start with a trapezoidal sum, and you have to read the text to see what it's asking you for. Okay, so in this case, we want a trapezoidal approximation for this integral using 4 subintegrals, or subintervals rather, as indicated by the table. Okay, so the 4 subintervals, so 1, 2, 3, the 4 subintervals are always between each of the x values. Okay, so what this is saying, let me draw you a sketch here. So we have a bunch of points, and these are kind of a rough sketch of the data in the table. And what we're trying to do is figure out the integral involving these points. So this table could be anything. This could be like a distance, or a speed problem rather, like we saw in the introduction to this unit. This could be a rate of change in other contexts. But this is why this is useful. These approximations are useful because I can take a data table and I can make estimations or claims based on an original function. Okay, so what we're going to do, this is my table, we're going to think of turning my table into a bunch of trapezoids. So here's trapezoid number 1. Again, this is going to be a rough sketch. Trapezoid number 2, trapezoid number 3, and trapezoid number 4 is going to be very small. So we want to find the area of each of these trapezoids in order to make a guess at what this integral is. So let's do that. Remember I said in a previous lesson that the area of a trapezoid is 1/2 b1 plus b2 times the height. That's exactly what we're going to do here. Okay, so the bases, well actually let's start with the height. The height is going to be the change in x. So I'm going to write that as delta x for each intervals, right? So this first interval from 7 to 3 is 4, right? 10 minus 7 is 3, 13 minus 10 is 3, and then 14 minus 13 is just 1. Okay. b1 plus b2, well, these are the f of x's. Okay, what do I mean by that? Well, this point would be 3, 18. This point would be 7, 17, right? So these f of particular x's are the height, or the height of the function, but in this case they're the base of a trapezoid. So we're thinking of a trapezoid as turned on its side, right? And then the 1/2 is just part of the formula that actually comes from, believe it or not, the formula for the area of a triangle, because we know that these guys are rectangles with triangles on either end. So let's take a look at what this is going to look like. So we're going to use this formula 4 times. So the first one is going to be, actually let's do this. So this is our trapezoidal sum. So take a second to look at this. Trapezoidal sum. So these are the 2 bases of my trapezoid, in this case 18 and 17, right? Over 2 is the same as saying times 1/2. Times 4 is that change that we saw. So notice these guys, 4, 3, 3, 1, are the changes on the x-axis, and each of these are going to be the y's of the points. Then we're just going to substitute and solve. So this is what that would look like. Notice I've just plugged in values from my table, right? So my f of 3 and my f of 7, well that's 18 plus 17 18 plus 17, right? And I continue to do that throughout the table. And I'm just going sort of interval by interval, right? So my first trapezoid is this first interval. My second trapezoid is this second interval now. So they kind of overlap in a certain way. So you go from 7 to 10 for that second one. And then I calculate the area of each. And then I just simplify. Okay. So that's a trapezoidal sum. So take a second, check your understanding in your head. Ask yourself, do you really understand this or not? And then capture all of this in your notes. Okay. I know there's like a lot of intermediate steps, but capturing this is going to help you on the problems for sure. Okay, make sure you go back and capture the rest of that. If that was not enough time for your notes, you should pause the video probably. Here, we're going to do a midpoint sum. Midpoint sum approximation for this guy. We're going to use 4 subintervals. So this is different now. Notice we have 4 subintervals that we want, but there's a whole lot more intervals in the table. So let's remember what we're thinking about here. I'm going to draw you a sketch. I'm not going to sketch all of these points, but what we're doing is if we have a function, we're drawing rectangles so that their midpoint ends up on the function. Right. And this seems like it may be tricky. Like we're going to have to divide points by 2 or find their average or something. We actually don't have to do that. So they give you enough information for that. So notice 4 subintervals. And there are 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 x's, right? So I'm just going to essentially pick every other one. Because if I do that, I'm going to get 4 points to use. So 2, 6, 10, and 14. Okay, so those are going to be the midpoints of my 4 subintervals. And notice like my subintervals here are going to be from 12 to 16, 8 to 12, 4 to 8, and 0 to 4. So what I'm doing is I'm making rectangles out of these, and that's going to look like this. So I'll show you the solution here. Okay, so notice f of 2, my midpoints that I picked show up in each of the rectangles here. The math here is, of course, simpler because rectangles are an easier shape to find the area of than trapezoids. Okay, so my midpoints show up, and then notice they have 4 each time. Well, how do they get 4? Well, this 4 minus 0, so that's the change in x. This 4 would be 8 minus 4. This 4 would be 12 minus 8. And the last one, of course, would be 16 minus 12. Okay, so this 4 is, again, the change in x. And then this f in each time now represents the height of the triangle. So this is f, and then this is change in x. And then I simplify all of this and add them up. I get 124 is my approximation. And that's my approximation for this integral. I don't have to worry about whether it's an over or underestimate because we don't have precise knowledge of how that works with midpoint Riemann sums. Okay. Again, make sure you have this example captured, including, I think it would be good to capture these notes about where these 4s came from so you're not confused later. Pause the video to do that, and then when you're ready, unpause and we'll move on. Alrighty, here we have a left Riemann sum. Here's where we're going to start to really have to think about left versus right Riemann sum. So I'm going to draw you a sketch to remind you of what we saw in the last lesson. We're going to use 3 subintervals here. So let's say I have a function. My left Riemann sum means that I'm estimating using rectangles. And the left side of the rectangle is on the function. Okay, let me make this a little bit better. Okay, so that's a decreasing function, and notice we have an overestimate here. And that's what we got here is a decreasing function, right? So x gets bigger, y gets smaller. Okay, so let's think a little bit more about what we're trying to do here. So we want to use the left points of our rectangle as the height, right? The width of the rectangle is going to be the change going to the right of that, right? So in this case, we'd have 2, what do we have here? We'd have 2, and then 6, and then 10, 12, and then we'd have, at this point would be 21, this point would be 4, right? This point would be 10, and this point would be 5, but we're not going to use that point. Okay, so, because 5 would actually be down here on the actual function, right? Okay, so let's look at the area of each rectangle. So from 2 to 6 is 4, and then the height is obviously 21. From 6 to 10 is 4. The height is also 4. This is not to scale, obviously. And then from 10 to 12 is 2. The height is also 12. Oh, sorry, the height is 3. Okay. So I've used, well, let's see. I used from 10 to 12. And then I used from 6 to 10 was my second interval. And then I used from 2 to 6 was my third interval. Alright. And then from those, I used the left-hand y value, the left-hand value of f of x for the height of each rectangle because it's a left Riemann sum. So I use the smaller of the two after I pick my subintervals. Or the one that goes with the smaller x, rather. Okay, let me show you the solution here. Okay, it's exactly what we just did, right? So if you just look at this, it's not 100% clear what they did, so a couple notes I'm going to make. So this we picked because it's the left corner, and that's true of all of your f's. And then these values, these are our changes in x for each, right? So this is 6 minus 2. This is 10 minus 6. And then this is 12 minus 10 is how they got to. So be very clear why they picked what they picked. And make sure you capture good notes, including my little annotations here, because that will help you set these up on your own. Make sure you've done that, you have good notes, and then we'll move on to a right Riemann sum. Okay, last one. Right Riemann sum. I'm going to draw a sketch to start, just like we started the last one. A right Riemann sum. Let's see, we have an increasing function, so I'll draw an increasing function. A right Riemann sum, remember, has the corner of each subinterval on the function. So that should not look like that, right? So the corner of each subinterval being on the function means in this case, most of our rectangle is above the function. 3 subintervals in the table. Okay, so what we'd have here, right, is from 3 to 6. I should have left a space here for like 0 and stuff, right? But from 3 to 6 would be a width of 3. From 6 to 9 would be a width of 3. 9 to 13 would be a width of 4. And then for the height, we're going to use the rightmost side. So height of 6 in this case, because I'm using this value. A height of 19 in this value. And then a height of 30. So my 3 subintervals are going to be from 3 to 6, from 6 to 9, and then from 9 to 13. And then this time I'm using the higher of the two x values to pick the height of my rectangle. So that would be 30 for that subinterval. That would be 19 for that subinterval, and then that would be 6 for the last one. So let's take a look at what the solution looks like. You can probably predict at this point what it's going to look like. So f of 6 times 3, f of 9 times 3, so exactly what we expect, right? That's would be like the purple highlight, and then f of 13 times 4, that would be the orange highlight here. And again, those numbers that they got, each of those is a change in x for each interval. Then you just make your substitutions and solve. Okay. Big lesson, guys. So make sure you have notes for all 4 examples. You're going to have to figure out which steps to use as you do these on your own. So make sure you're referencing those notes as you go.